All right, so finally we're at the section where all of this stuff comes together and we get something that's actually worthwhile. This is my favorite section in the entire textbook. We're dealing with exponential growth and decay situations. Situations where things are growing exponentially or decaying exponentially. Things that grow exponentially would be like your bank account that grows by the same percentage every year, assuming you're not putting money in or taking money out. The spread of diseases, where each person would infect two more people, that's going to be an exponential growth situation. Exponential decay is like when something's cooling off. You take something out of the oven and put it in a 70-degree room and it starts to cool off, but it cools off faster at the beginning and slows down towards the not towards the end, but as time goes on. And we'll see what that shape of that graph looks like in a few minutes. I want to take a look at the equation first. The equation for straightforward exponential growth or decay is this one here. The population, or whatever thing it is we're looking at, they tend to use P for this, but it could be temperature, it could be population, it could be number of infected, it could be all kinds of things. The amount of whatever after T time periods, be it days or years or whatever, is the original population, wherever the thing started at, times E to the product of the rate, how fast it's growing, that's going to be as a decimal, times the amount of time that the thing has been growing or decaying. So it's very simple. It's just where it started, E to the rate times time. And if you have a positive rate of growth, this thing will grow, or if the rate is positive, this thing will grow. If the rate is negative, will decay, and we'll look at an example of each of those. And little formula here for the doubling time. I really don't care about doubling time, but my math lab asks 5-part questions, and if you don't get one of them right, you don't get your green check mark. So this is really here so you can get your green check mark. So let's take a look at just a basic generic situation here. Let's say we're going to have something growing. Let's say we've got something starting at, say, 100. And 100 times E, it's going to grow at a rate of 5%. So we put in 0.05 times T, we have to use X, of course, and close the parentheses. We get the original thing, E to the rate times time. Now, if we're going to look at a graph of that, of course, we're not going to see anything because our numbers aren't between -10 and +10. So we go to Window, and we do what we always do, X min to 0, Y min to 0. X max to, let's look out 20 years in the future, just cause, nowhere to know where that came from. I just decided 20. But how high do we think that bank account is going to get after 20 years? Started at $100, 5% a year. Maybe get up to something like 200. So let's set our Y max at 200. And we're starting at 100, and it's going to get bigger and bigger. Not only does it get bigger, but the rate that is getting bigger at increases, right? It keeps curving upward. That's the nature of exponential growth. Let's look a little farther out. Let's look at this over, say, 100 years. It's going to get much bigger than 200. Let's put that top at 1,000. Okay, so it starts off growing at one rate and then really picks up. When you hear people talk about exponential growth, most of the time they mean something is growing quickly. What exponential growth really means is growing like that. So let's go back to our equation. And if we change that 0.05 to a negative 0.05, we'll get quite a different looking graph. I'm going to set Y max at 110 because this time it should be decaying. If it starts at 100 and it decays, I shouldn't need to go any higher than 100. So it decays and it levels off. That is exponential decay. And that's what happens. You take something out of the oven at 150 degrees, you set it in a 70-degree room, and it keeps getting closer and closer and closer to room temperature, finally leveling off. As opposed to linear, which would keep getting colder and go right past the temperature of the room and into freezing, which wouldn't make any sense. That's why we need exponential growth equations to take care of this kind of stuff for us. Now I'm trying to keep these little pieces short, so I'm going to stop here, and in the next one we're going to look at a couple of these word problems right out of the book.